To help you improve your problem solving skills on Codechef, I have decided to start this CC reflection series where I will take a look at a recent Codechef problem and walk you through my thought process of solving that problem. Let's consider problem Kill Monsters from Codechef Starters 149. You are given several monsters with some health and you start the game with an initial power of X. In each round, you can select any monster whose health is strictly less than your power. You can kill that monster forever and your power will get reset to the health of the monster that you just killed. Your goal is to find out the maximum number of monsters that you can kill in this game. However, there is a special operation that you can apply only once during the game if you want. And the operation is that you take your current power and you multiply it by some number k which is given to you. This is the problem statement. Feel free to pause this video, read through the problem description and try to come up with a solution before watching the rest of the video. Note that this problem has two versions, an easy versions where the constraints on health and the initial power are quite small, and a hard version where the initial health and the power can go to 10 to the power 9 or 10 to the power 18. Let us try to solve this problem when there are no special operations involved. Let's sort the health of all the monsters in increasing order and let us locate the first monster that we cannot kill. This can be easily done via the lower bound function in C++, and we will call this as an unsafe index, and that is why it is colored in red. Now, it is clear that all the monsters to the right of the unsafe index cannot be killed as well because their health is strictly greater than your current power, and you also know that your current power will only decrease in the future. Since it will only decrease in the future, this is your best chance to kill this highest health monster. So you should kill it right now. But if this monster has two copies, you cannot kill both the copies. So you should kill one copy of this monster, and then this is your best chance to now kill one copy of this monster and finally one copy of this monster. Now you can see that the total number of monsters that you can kill when there are no special operations involved is equal to the number of unique health monsters to the left of the unsafe index. But what happens if you are allowed to do this operation at most once? Since your power will only decrease in the future, if you try to do the operation right at the start of the game, that multiplication might land you over here. This might become the unsafe index. But if you wait for the future rounds and your power has decreased, then if you multiply it by k, that jump might lead you to this unsafe index. So it is clear that the number of unique elements in this range is obviously smaller than the number of unique elements in this bigger range. So it might look like that it is always optimal to do the multiplication operation right at the start of the round. However, we are missing something obvious. Can you think about what that is? Feel free to pause this video and think about what we missed. Suppose k is equal to infinity. Then if you decide to do the jump at the start of the game, it will lead you to the end of the array, and from there you can take one copy of all of these unique elements. However, if you don't be greedy and follow the rules of the game normally to kill one copy of this monster, one copy of this monster and one copy of this monster, and from here if you make a jump which will lead you to the end of the array again because k was equal to infinity, you will notice that you can take one copy of each of these unique elements. However, in this process we were able to take an extra copy of this green box, blue box and this teal box. Therefore, this jump provides you the opportunity of taking more than one copy of some elements, and this count might exceed the number of elements that will leave out by not making the jump at the start. So there is a trade-off, and that is why it is not optimal to make the jump at the start of the game. So where should we make the jump? Is it this index or this index or this index? Let's not guess. Let's try to make the jump after killing every monster in our first trip and take the best possibility out of them. Now notice that you are making 2 trips, and in each trip you will only kill one copy of the unique elements. Therefore, it is clear that for each color you can kill no more than 2 copies. But we can say something stronger than that. If this is the unsafe index, for all the elements on the left, they can be encountered either on the first trip or on the second trip. So you can have a maximum of 2 copies. But for all the monsters on the right hand side of the unsafe index, they can only be encountered on the second trip. Therefore, you can only have a maximum of 1 copy of these monsters. So let us maintain an alive array where we will record the number of alive monsters for each color, and the values in the alive array can be at most 2 in this segment, and it can be at most 1 in this segment. Then let us follow the rules of the game normally by killing 1 copy of each safe index that we have and keep going left. As soon as we decide to do an operation at this index, what will be the total number of monsters that we can kill if you decide to do the operation over here? It will be equal to the number of monsters that you have already killed in the first trip plus the number of alive monsters in this segment. Now notice that the number of alive monsters in this segment now cannot be more than 1, because you have already killed 1 copy of the monsters in this segment and these were already 1, right? A maximum of 1. So it would be equal to the subarray sum of the alive array plus the number of unique elements to the left of this color. Then you can simply do this operation at every monster after killing it and look at the best answer that you can get. And in the easy version of the problem, since the health of the monsters was at most 5000, you can simply iterate backwards to calculate the sum of the alive array, which would denote the number of monsters that are still alive after the first round. This is the code for this problem. First of all, we figure out the frequency of each color and we restrict it to a maximum of 2. Then we arrange all the unique colors in a straight line in increasing order of their health, and we also create the corresponding alive array from the frequency array that we just created. Then if we decide to do the operation right now, it will lead you to some unsafe index and the number of unique colors to the left of that color will be your answer. But if you don't decide to do the operation right now, then you should locate the unsafe index for the current power X that you have, and all the monsters to the right of this color can only be encountered on your second trip, so you set its alive count to a maximum of 1. Then for each safe index to the left, you keep iterating over each unique color that you encounter and you take 1 copy of that monster and you update the alive array. And after taking each element, you try to make that jump and see what answer can you get. So what is the answer that you can get? It will be equal to the number of monsters that you have already taken, which is stored in the variable called taken, plus the number of alive monsters in this range, which is simply the subarray sum over here. So this is simply the subarray sum between the 2 jump points, plus the number of unique colors to the left of this color, which is nothing but the index of this color in that unique colored array that you have created. So this is the profit that you will get, and then you take it to be the maximum of all the jump points that you encounter. So the time complexity would be O of n square, assuming n to be the number of unique health monsters. How do you optimize the time complexity when the number of unique colors can be large? Notice that our bottleneck is how to update the alive array and query the sum of it, because in the first trip that we are making, we are decreasing all elements of the alive array in this region by 1, and at every point we are querying the subarray sum between these jump points. And a segment tree is the perfect data structure that can allow you to modify elements and query this sum of a subarray in O of log n each. And if you are familiar with Coder library, for which I already have a tutorial on my YouTube channel, you can simply use the segment tree from Coder library as a black box. So I'll just put this code on the screen for you to pause and read through. So I usually like to wrap the segment tree in a custom class and then use it accordingly in whatever function that I require. So the only change would be take the old code from before, and instead of querying the sum manually by iterating backwards and computing the sum of the alive array, I can now just call my segment tree with the jump points, and I will get the time complexity of n log n. Even if you are not familiar with segment trees, you can still do this optimization. Notice that the decrement on the alive array are in a specific order. That is, you locate the first unsafe index, then decrease this element by 1, then this element by 1, then this element by 1 in your first trip. And the queries that you do on the alive array to compute the sum of a subarray, they are also in a specific order. That is, they will always be to the right of the last element that you just decreased. Therefore, you can solve it using a suffix sum. But if you naively implement the suffix sum array by computing the suffix sum array for the entire array at the start, then you might face the issue of updating the suffix sum subarray whenever you do a decrement over here. However, notice that when you do a decrement over here, nobody will query for the subarray sum for this range. That is something that you are guaranteed. Therefore, you can do an incremental build of the suffix sum array in a lazy fashion while ensuring that you always return the correct answer for the suffix sum on this region, but you don't care about the correct answer for this region. So whenever you do a decrement over here, notice that the suffix sum array of this segment will not be affected. So you just need to refresh the suffix sum value of this segment, and that is it. Then when you do the decrement over here, these suffix sum will not be affected, and you just need to refresh this suffix sum value. So you just have to build the suffix sum, and if you want to compute this subarray sum, the answer will be equal to the longer suffix sum minus this shorter suffix sum. And this is the code for this problem. It is just a simple wrapper where instead of a segment tree, we now have a suffix sum array, and every time we do the update of an index, we will only need to update the last element of the suffix sum array, not rebuild the entire suffix sum array. And this is how you compute the sum of elements in a range. And for the operation, we will simply replace segment tree with our custom data structure for suffix sum. Competitive programming is all about innovation and creative thinking. While we were too focused on the complicated data structures such as segment tree and suffix sum, there is a very easy and elegant solution to this problem that we have missed. Notice that we decided to figure out the answer for each index in the order that we encounter it during our first trip. And then we also decided to make the first trip manually in the hopes that it will lead us to compute the answer for the second trip very easily. But in fact, it is even easier to solve the problem if you decide to compute the answer for any index in a random order. So for example, suppose you want to compute the answer for this index, that is, this is the jump point that you have. Then, and now also suppose that you have not made the first trip. Then if this is the new unsafe index, this blue element over here, what is the total number of elements that you would kill in this range? It will actually be equal to the subarray sum of the unmodified alive array. Why? Because we have already discussed that there can be a maximum of 2 elements in this range towards the left of the unsafe array, unsafe element. And since this segment will be encountered twice in our trip, both these monsters can be killed. And in this segment we have already discussed that there can be a maximum of 1 monster for each index. So since this segment is encountered in the return trip only, these monsters can also be killed. So every monster represented in the alive array of this segment can be killed, and the answer is simply equal to the sum of the alive array. And what about this segment? This segment will still be encountered in just one single trip, which is equal to the number of unique elements in this range. So all you have to do is create a prefix sum array to answer the subarray sum queries faster, but you do not need to do any updates to the alive array. Also, you can solve it using 2 pointers instead of using lower bound to find out the next unsafe index. Why? Because the unsafe index will be in decreasing order. Another thing that I wanted to point out is, look at the constraints for the health. It is up to 10 to the power 18, and constraints for k is up to 10 to the power 9. So why do we not need to worry about multiplication overflow? Because it can go up to 10 to the power 27, because we are doing the multiplication operation at each of the index. So do we need to worry about the overflow? Actually, we do not need to worry about overflow, because we are only doing the operation on these safe index, and safe index will be obviously smaller than the unsafe index, and this unsafe index can be maximum 10 to the power 9, because we are using the lower bound of the initial x. So that is why we don't have to worry about the overflow. So I will add the code and slides for this video in the comment section. You can also find it in the in cfstep.com, and I will also link it in the YouTube comments down below. Just for the sake of completeness, this is the code for the version with the prefix sum. So I just have a simple data structure for prefix sum, and here I use the data structure to compute the sum of the alive elements between these jump points. But there is a small catch, that if this jump point is towards the left of the initial unsafe index, then the elements in this range needs to be counted exactly once, because they will be encountered only on a single trip. So that is why you compute the number of unique elements in that range.